All right. So we started with introducing you to the pipelining in the last session, and I hope you understood what exactly is pipelining. I told you pipelining is all about having multiple instructions being executed in parallel, and I took an example of a washing machine, a dryer, an iron, and these three are used by one person if they are all together as one equipment, and these three are used by three different persons at the same time so that there could be increased productivity on the whole. I explained you this clearly, I believe, in the last class, and I hope you all understood it. If you have any queries on this, you can let me know. I'll be able to clarify it. Now, the pipelining on the whole will reduce the overall, will increase the overall efficiency in terms of throughput, but no individual load. Man A will still have to spend the 30 minutes, man B will still need to spend 30 minutes, and man C again will be spending 30 minutes. So it is not an individual's performance which is going to be improved. Instead, it is team's performance which is going to be improved overall by a very nice extent. That's what we learned. What exactly is pipelining is all about in the previous session. Also, there was a catch that we need to understand when it comes to pipelining. It is all about making sure that we have three independent equipment available. This is an independent equipment, this is independent equipment, this is again independent equipment. So this could increase our cost by a bit, but if you want the luxury of having pipelining, if you want the luxury of having parallel execution, we must go by this and we must adhere to this. There is no option. Right. With this simple recap, I'm getting into today's session where we are going to go a little higher in terms of understanding, as well as we will understand the math a little bit. Right. Okay. What are the stages in pipelining? As you know, the first stage is called fetch. I am going to fetch the instruction from the memory. This is the first step. I am going to fetch the instruction from the memory. From here on, fetch is always represented by if. You should not change it, and I am going to use the terminology if. The representation is if, which represents instruction fetch. So remember it, the first stage is instruction fetch. What is the second stage? The second stage is nothing but decoding the instruction. Remember, MIPS will permit you to decode and read register at the same time. You can decode and read the register content at the same time, and it is very important, and we are referring to the decode with the code ID. ID refers to instruction decode. This is also very important. Now, I have an instruction. I understood that I am going to use register R0 and R1 or MIPS terms S0 and S1 or T0 and T1, and I am going to add them together, and the result has to go to T3. So I understood what all the instructions all about, what is the instruction all about, and what all the registers which are going to be used. So what is the next step? The next step is obviously execution. So I need to go with the execution stage, and it is represented by terminology EX. Remember, it is represented by EX. EX always refers to execution. And right. The next step is all about memory. What do you mean by memory, sir? Very simple. If it is a load word or a store word instruction, I need to obviously access the memory location, and it is represented by MEM. That's it. And the last stage is represented as write back. It is called WB. What do you mean by that? Very simple. The result in the hand has to be returned back to the registers, and that is represented by characters WB. Now remember one very important point, we cannot change these notations. We will have to follow the notations of IF, ID, EX, MEM and WB properly. When you are asked to draw the pipelining structure, this is the way you got to draw. First time IF, ID, EX, MEM, WB will be there. Second time when it is ID, you need to put IF. Third, when it is EX for the first instruction, second instruction should be in ID, third should be in IF. Likewise, you need to follow a staircase model. This is like a staircase. Remember it, and this cannot be changed at any cost. Do not change it. Sir, I created my own notation. Can you give mark? No, we cannot give mark. This is the notation that we need to follow. So just blindly follow this, okay? Do not change it. Now let's get into some mathematics. We are going to take the single cycle and pipelining comparison right now. I am going to take single cycle and pipelining as a comparison. Now let's understand that we have got four instructions. One is load word, another one is store word, and it could be add, sub, or and BEQ or BNG. These four instructions are pipelined one after another, I mean stacked one after another to be executed. We are going to go with single cycle execution, or we are going to compare the single cycle execution alongside the pipelined execution. Now they have given the 5 stages. You can see that here: fetch, decode, ALU, memory access, write back. Now fetch, decode. You can see that the decode stage can also permit you to read. That's what I told you here. Remember it, MIPS always permits you to decode and read registers at the same point of time. MIPS always permits you to do that. Remember it without fail. This is the most important point to be remembered. Now it can be read or it can be decode. It can happen together. Now what is the total value here? 200 plus 100, 300, 500, 700, 800. So total time required for execution of the load word instruction is 800 picoseconds. I need 800 picoseconds for me to execute, for me to complete the execution of the load word instruction. Now what is the next thing, sir? I am going to go with store word. Store word needs 200, 100, 200, 200. I do not have any write back in terms of store 100, I mean in terms of store word. So I get 200 plus 200 plus 200 plus 100, 700 picoseconds as the total time. Similarly, for AND, if you see 200, 100, 200, no memory access required for AND, and I go with write back for sure, so I need 700. Similarly, BEQ I have calculated 500 picoseconds. Remember, whenever the question is given for this kind of analysis where you have all the 5 stages mentioned, the first thing that you need to validate is if all the stages are appropriately mentioned correctly. For example, in the add instruction, if I have mentioned something as 100 picoseconds here, the question itself is wrong. In the store word, if I mention 50 picoseconds here, the question itself is wrong. So I might purposefully give a question which can test your understanding, as in have you understood what are all the stages, what are all the access that are going to happen, what are all the contents that are going to happen on each instruction execution. So please do go through the question and understand if everything is proper. If it is not proper, there itself we need to put it on a hold, saying that this question is wrong, I need a right question. There could be an option in the question saying that none of the above or the question is wrong, something like that. So be careful about it. This is a very important point to be understood. Now we are going to assume something. Each stage from here to here, here to here, there could be some delay. Definitely there could be delay, because it is like I have a washing machine, I wash the clothes, I now have to move it to the dryer, and I need to collect it into a bucket here, and the bucket's content only go here. So it will take at least 5 seconds for me to do this transaction. So what I convey here is very simple. Any instruction from one stage to another stage, when it goes, there could be a minor delay, and we are not considering the delay here because it would increase the complexity. Sir, where can the delay come, sir? The delay can come in even the multiplexers, because the multiplexers have to process. So there could be a delay in between. So whatever example I gave you is a very simple reference of a real-time example. You cannot just like that move all the clothes that are washed immediately into your next stage where you are going to dry it. So what you are going to do, you are going to take a bucket and you will put it in the bucket, and then you will fill it up in the next stage. So that's the delay that you can anticipate there. Similarly, here the multiplexer has to select the next stage where the input has to go. What will happen will have to be checked by multiplexer, and we are ignoring that delay, because when you include that delay, the processing would be slightly confusing or slightly delayed for you to understand theoretically. So let's ignore it right now. Now, what are we going to do, sir? We are going to compare for single cycle as well as pipeline execution model right now, and that will give you a very clear clarity as in what is happening at each stage. So remember it, this is a very important point. Again, I'm telling you, all these are to be read once again. Whenever you have free time, please read it through. Otherwise, the entire learning goes in vain. So please read it through once more, all of you. Now, what is the first thing that I told you? I am considering no delay for the multiplexer. That's the first thing that you need to consider. The second thing, in single cycle instruction, I am having a single cycle model. Each instruction will exactly need one clock cycle. Each instruction will exactly need one clock cycle, and this is the most important point. So remember, the clock cycle should be stretched as much as possible to accommodate even the slowest instruction. Sir, I need one clock cycle for each instruction, and the clock cycle should be accommodating even the slowest of instructions. There could be one instruction which is very fast, there could be one instruction which could be slow. So I need to accommodate both fast and slow instructions. Can I give you an example here? I have two students, A and B. A is a fast learner. He learns the concepts in say 10 seconds. B is a slow learner. He needs 20 seconds for learning. I am the teacher. So now I cannot teach them separately. So what I do is I make sure that both of them are accommodated and I will have to spend 20 seconds only. In that 20 seconds, this guy may complete the task in 10 seconds, but as a teacher, I need to make sure that I also lift this guy properly. That is it was I'm saying that is the same thing that I'm saying right now, but in terms of clock cycle. I have to accommodate even the slowest of the instruction properly. For that, I may have to stretch the clock cycle. I'll show you how do we stretch it and what exactly happens over there. Now, out of these four instructions, load word, store word, add, BEQ or BNE, which is the slowest of the instruction? 800, 700, 700, 500. Fastest is BEQ, forget it. The slowest is load word. So, 800 is the slowest, which means load word is the slowest of the instruction that I need to look into. So 800 picoseconds is the slowest. Now, since we have to accommodate all the instructions and we need to accommodate even the slowest of the instruction, the time required for load word is going to play a vital role. So, the time required for the load word would be the time required for all the instructions, because I have to stretch the clock cycle in such a way that it can accommodate the slowest of the instruction as well. If I have time for 800 seconds, obviously 700 seconds instruction can run there, 500 seconds instruction can run there. So what I mean is I need to accommodate the slowest of the instruction so that every other instruction will get into execution easily. Now 800 picoseconds is the longest and that is the slowest in fact. So I need to make it as 4 instructions are here. So I need to make it as 4 into 800, which eventually will get you 4 into 3200. Here it is wrong. This is correct. Now, otherwise you can cite it like this. The difference between the first and the last instruction, something like that. So, this is actually cranky. This one can be forgotten. This is the right way to mention it. So, I need 3200 picoseconds is the total time. When I go with single cycle design, I will need 3200 picoseconds for me to execute this sequence of instructions. Now, let's go with pipelining. What is the case, sir? Very simple. I am taking the same scenario. Here you could see that I made it 800, 800, 800. Likewise, I kept on moving and I had to go with 3200 picoseconds for a non-pipelined architecture. Now let's come into pipelined architecture. The first instruction is here. You can see that there is a gap here. Second is here, third is here, fourth, fifth are here. Now the second one, there is a gap here. You can say, I'll tell you why the gap is there later. Don't worry about it. Gap. Now, if you see that, we have completed the entire flow by say around this time frame. Earlier it was 3200 picoseconds. Now it is somewhere between 1200 and 1400. Sir, what is this 200, sir? You did not explain. I'll explain you all that clearly. Just hold on. For now, just understand one point. It is nothing but pipeline architecture is always better. It is always faster. Now, what is the first stage? First stage is load word, 200 picoseconds. What is the second stage? Second stage is here, and that is nothing but I'll have to decode and read. So 100 picoseconds. Now you see that I am going to, if you see that previous table carefully, this is a read and decode. This is read and decode, both happens. So you need to understand one point here. I hope some of you would have understood right now. When I am reading, I'll have to do from the right. When I am writing, I'll have to go to the left. So when I'm, let's forget this right now. I'm not going to confuse you right now. Let's keep it as such. In this case, you remember that this is complete and this stretch needs 100. So, but you cannot do that way. What we are planning to do is, what we have to do is, the longest of duration here. Which is the longest of duration here in this? 200 is the longest of duration. So each stage would need only 200. So you can see that here it is all 200 here. Instead of you allocating the overall execution time of 800 for all the instructions, here it is going to be stage by stage, and that's what we have given. One second, something has happened. Let me go back. I'll share this PPT shortly, don't worry. You can go through it once again, and once you go through, you will be able to understand. This is very simple, this is not complex at all. I'll explain you once again, don't worry. Now, the most important point that you need to understand is, in the pipeline instruction, the worst case clock cycle of 200 picoseconds per stage would be considered. So this needs 200, but here I need only 100 as per the problem statement, but I'll have to make it complete. I'll have to make it 200 only. This period will be wasted, but still that is fine. So this is that period that is getting wasted. This is the period that is getting wasted. Here we completed, so I did not have it here. I complete the 100 seconds here. I complete the writing process here. Here it is. So learn this way. When I'm going to read, it has to happen from the right. When I go into write, it has to happen to the left. So you can see that here, this is writing, this is writing, this is writing. So I fill the content to the left and I cut this part. But when I am reading, I need to move it here, and the first 100 seconds, the first period, first half should be left empty. So remember this is very important, and we will have more examples on this pattern. So if you cannot understand right now, don't worry, we will explain it again. The point is simple, every block will be 200 because 200 is the maximum of the duration, and I will have to go with 200 for each of the stages. So the worst case, if you see, the amount of time that we have spent is not more than 1300 seconds, 1300 picoseconds. Earlier it was 3200. Earlier we considered the longest of duration for the instruction itself, and we had to allocate that. Now we are going with stage wise, and we are just picking that particular stage and we are allocating that time to accommodate all the stages properly. That's it. Now the point is very simple. When you go with pipeline architecture, the time required is definitely lesser. The time required is certainly much better than the time required for a single cycle design. Now let's go with the formula. We need to understand a formula, and we need to understand how do we calculate the time between the instructions. Time between the instructions for pipelined architecture has to be calculated by the time between the instructions non-pipelined by number of pipe stages. That's all. This is how we need to use, and we will use this sometime later. Just remember this formula. For me to calculate the time between instructions for pipeline stuff is nothing but the time between instructions in the non-pipelined architecture by number of pipe stages. That's it. You will have to remember this, and we may use this sometime later. Till now, do we have any questions? I would be happy to take up the questions. Right, all of you please go on mute again. I hear some echoes. Right. So let's go into the next topic, which is very important. I will introduce you to the topic today, and we will go ahead in detail by tomorrow, because again it needs a lot of time. I am going pretty slow. We will understand this very clearly over a period of time. I am telling you, right, pipelining, if we complete, we are almost done with the subject. It's so very important, and it's very interesting as well. So make sure that we guys spend a lot of time in understanding all this properly. What is a hazard? Okay, I am the person A. I am trying to complete a distance of 1 kilometer by walking, and this is the destination. This is the destination. In between, there is a big pothole on the road, so I cannot travel. I am stopped at 500 meters. Now this is a hazard. Do you understand? A hazard is something which is not letting me go to my target, which is not letting me reach my target. That's all is called as a hazard. A hazard is nothing but which can stop us to go to the next stage. That's called hazard. Remember it. Now, with respect to computer architecture, with respect to pipelining, we need to understand what is a hazard. Pipelining and hazardous situation is a very famous scenario, and very famous and very common interview questions. So please listen to it carefully. If at all you do not understand, I will be able to explain you again. If you understand it at first shot, I am very happy. Let's understand. What is it? Very simple. In pipelining, there are 5 stages. Stage 1, 2, 3, 4 and 5. Likewise, for every instruction it happens. If the next instruction cannot be executed in the next successive clock cycle, I call it a hazard. I have got first instruction, the first instruction 5 stages are there. I have got the second instruction like this. I've got the third instruction like this. Now what happens is, if this cannot be started while this is being done for some reason, I could call it a hazard. If this cannot be started while this is being done, I could call it a hazard. Anything which prevents you from getting the navigation done to the next stage is called a hazard. Do you understand that? A hazard is something that stops your progress. We call it hazardous, right? Don't watch TV so much, it is hazardous. Don't be in FB so much, it is hazardous. Just like that, we are calling this hazardous because we are not able to move to the next successive step. That's it. Now let's get into the point very simply. There are 4 types of hazards. There are 4 types. Remember, all these are very important and we are going to go step by step. The first hazard that we are going to learn is called structural hazard. The first hazard is called structural hazard. The term, when it calls as structural, you could have by now understood that it is related to hardware. Whenever we have something called as structural hazard, close your eyes and determine that it is a hazard which is connected to hardware. That's it. Now, let's understand the term further. The structural hazard is something which is going to not let you do the next step, but this will happen because of a hardware malfunction or a hardware unavailability or hardware incapability. I can call either of these terms properly, but it is dependent 100% on hardware and it is going to stop the progress. Right. When the hardware is not capable of supporting the combination of the instructions, when the hardware is not capable of supporting the sequence for the flow of instructions, I call it as hazard. And this type of hazard is called as structural hazard. I'll tell you an example so that you can understand. Let's take the same example of the washing scenario that I told you some time back. There are 2 separate equipment available in the previous case. I have got equipment 1 and equipment 2. Once this is done, I threw it into this so that the next person started using this. I mean, I have got 2 instructions. I have got 2 separate hardware available. The first instruction used the first hardware, then it moved to the second, and then the second instruction started using. This is what I told you some time back, and I'm pretty sure that you guys remember it. Now, if in case these 2 are not separate and they are in the same box, they are in the same unit, the washing machine and dryer are together available as a one unit. Now what will happen? Until both the stages are over, the second instruction cannot use it. Do you understand the point? The first person will be using the washing and he will immediately use the dryer section of it. Though the washing machine is not being used, he is still using the dryer which is attached to the washing machine, and hence he is not letting the next instruction execute. The next instruction has to wait until such time both the units are available, because both the units are appearing as one single unit. Remember it, it is all about getting the availability of the hardware resources. Though they are available, if someone is occupying it and someone not leaving it, it will become a hazard. I'll tell you an example. The first person has finished the washing. He has completed the washing process, but he went for a phone call. He attends the call and he has forgotten to take the cloths out of the washing machine. There are separate units available even then. He has forgotten to take the cloths from here. I cannot lift his clothes and I cannot keep it somewhere. It is not my duty, right? So what will happen? The second person will keep waiting until the first person is back from his call to lift the material. This is a hazard, and this kind of hazard is called the structural hazard, and you cannot get pipelining done easily whenever you have this kind of hazards. So remember, this is 100% related to hardware. Whenever the hardware is unavailable, or whenever the hardware is locked with one of the particular instructions and it is not releasing it for the next one to use, we call it structural hazard. Remember it, it's a very, very important question in terms of interview as well. What is structural hazard? Now, we need to understand one very important point. I am going to give you a simple example, and we will go ahead with the next hazard, or we'll go ahead with the explanation of further things very clearly. Now, The risk versus risk difference we have seen. MIPS naturally supports pipelining. MIPS naturally supports pipelining, and instruction set is constructed in such a way that they enable and they support pipelining. Listen to this point carefully. MIPS is a risk architecture where MIPS naturally supports pipelining concept, and this pipelining concept is this is enabled through the instruction set construction itself. So they have taken extreme care to make sure that the stages are constructed properly, the stages are curated properly so that the pipelining can be enabled. Now we will assume that we are having only one memory unit. We are having only one memory unit and we are not having multiple memory units. I mean dual memory units are not available. One for instruction memory and one for data memory for an instance, and we do not have it that way. We have only one memory. Now what happens? Let's assume this same scenario. When the first instruction is executed and when memory is accessed in the first instruction in the fourth stage, the fourth instruction will also need to fetch the memory, access the memory to fetch the instruction. So the instruction fetch, if you see that the instruction fetch and memory are colliding. Here I am trying to access the memory, here I am trying to read the instruction, both are in the same content. So here comes the problem. This is dangerous. So this is called a hazard, and this hazard has to be avoided, and this is called structural hazard. Do you understand? I cannot access this and this at the same point of time if I do not have two different memories. So without distinct components available for me, I cannot go ahead and look for pipelining. When you want pipelining, make sure that you have distinct components available and make sure that they are all available for rest of the stages to use it. The moral of the story is very simple. Whenever you go for pipelining, whenever you want to be done with pipelining, it will be expensive. Keep components separately. You need to have individual components and there is no other option available. Use individual components. The next one is data hazard, which we will see tomorrow. I am going to explain you the data hazard clearly with lot of examples, and this is the best part of your learning. I am telling you. Tomorrow will be very nice, and this is called as bubbling. I am going to explain you the complete data hazards only tomorrow, and day after that we will go with the control hazards. And if you learn the control hazards, then we will go to the pipelined data path. This is the most interesting part of your entire subject. I believe if you can understand all these properly, you can choose computer architecture as your favorite subject in your next interview process or your internship process applications, and that is that much interesting. Any questions till now?